Thank you. Thanks for that nice introduction. So yeah, Spur is the next generation of the COG virtual machine for Squeak, which started in 2008 to try and provide more efficient execution for the people doing the croquet shared 3D world stuff. And the key here is a new architectural idea, and I want to say something about the software evolution. But my goal here is to kind of seduce some of you to take a look at the VM and maybe get involved in the project. We're very, very small. We could do with lots of people to come and join us, and I hope to persuade you that it's a kind of a fun virtual machine to work on. So why Spur? So obviously COG was the name that I came up with, the original, and Spur, a Spur gear takes things off to the side, makes things faster, etc. Okay, so why should you be interested in Smalltalk at all, right? It's a dead language, right? Nobody's doing it anymore, right? Well, turns out that probably every single one of these was manufactured in a plant where every single machine in the etch, deposit, clean, except the initial lithography was controlled by a robotic system whose control software was Smalltalk. And it's very likely that it was delivered to your shop in a container that left China, and every step of the way along that journey, that container was being directed by a planning system written in Smalltalk. 60% of the world's trade is controlled with a Smalltalk application. BMW's entire parts catalog is a VisualWorks application. Deutsche Bahn compute their entire timetable every year. So Smalltalk is still very much in use in the enterprise. It's being a dynamically typed language with classes and substantial tool support. It can allow large teams to scale big programs and keep up with the rate of change in the real world. So it's around, and it's important. And why is it that Smalltalk does so well? So yeah, everything's an object, so you can extend integer. There's no built-in machine types in the system. There's no idea of a final class, although there are some classes that the virtual machine depends on that have to remain the same, that you can't change. And there's a really nice difference from many typical systems like JavaScript VMs, etc., is that because everything's an object, classes and methods are objects, the IDE can completely build itself in Smalltalk, and it exists outside of the VM above as a Smalltalk program that you can extend. So there is no compiler in the VM, there's no debugger in the VM. There's simply a system which is able to, by instantiating objects, which is a service provided by the VM, construct the entire programming system and its own organization and extend it. And so you get into this rather nice programming form where you can build tools while you're programming, not build tools, use tools, but actually co-evolve them with your program, which is very productive. And one of the real unique facilities in Smalltalk-like languages, which as far as I'm aware, is only available in Smalltalk Self and Newspeak, is this idea of activation records being objects too. So notionally, when you send a message to an object and you create an activation of the method that binds to, the virtual machine creates a little object to function as the stack and the execution of that one method. And a process is a spaghetti stack, a linked list of these activation records. And that has really nice implications. The debugger is not anything other than an inspector. And there's a metacircular interpreter. And again, the debugger is written as a Smalltalk program, and it can be extended as you go. And in fact, the entire exception system is above the VM. and exception search and exception binding is just normal message sending. Messages sent to these activation records. And then there is no control flow built into the language. There's no if statement, there's no while statement, etc. Because the language has a very lightweight closure syntax, and that there is polymorphism, and there's a little bit of support for performance, as we'll see. You can create arbitrary control structures in the language using only polymorphism and binding. So think of it as like expression if true closure, if false closure, right? This message with its two closure arguments is sent to an object which is either going to be true or false, and true implements, okay, evaluate the first closure, and false implements it as evaluate the second closure. Right? So polymorphism plus closures can give you control. But because the language was implemented in the 70s, there's a little bit of optimization so that in the bytecode, as we'll see, some closures have been inlined by the compiler into jump stuff. And then the other really lovely thing is that the way that the system is built is as a memory image, also known as a snapshot. And the memory image is the frozen objects at some state of the system. And that includes these activation records. So it includes processes which are in the process of that they're executing, but they've been stopped. And when you load your image into the VM, you end up with a live object stew. You've completely recreated your system, and you can have your windows open with exactly the state they had when you closed them. You can have inspectors tools open on partially completed computations, et cetera, et cetera. So you have this lovely way of tailoring your environment and taking it forward. So the Smalltalk VM turns out to be rather simpler than a lot of other engines, because it really is just an execution engine which executes bytecode. It's a set of primitives which implement the things in the language that you need, such as creating new objects, doing arithmetic on primitive types, etc. But also is your connection to the outside world, and might provide media primitives, etc. And then there's a garbage collector, but there's no compiler, there's no debugger, there's no parser, nothing like that in the VM at all. So let's take a look at the bytecode just to get an idea of the kind of the key architectural problem that we're trying to solve here. So if you'd see this in a browser, the top three lines, you wouldn't see point. Point would be sort of in the tool context. All you'd see is this less than a point. So what this is saying is that when you send a message less than with some object as an argument to a point, then the code underneath is what's written. And so we've got a comment that says, answer whether the receiver is above and to the left of a point. And so the caret is the return symbol. And what we do is fetch the instance variable x of a point. And we fetch whatever the object, the argument is, because we don't have any type information. And we send the x message to it. And then we send less than to the result of the instance variable x and the result of the computation. So we push instance variable 0, which is the x instance variable, and then we push the argument, the 0th argument, and then we send x to the argument, and then we send less than, and then here's the optimization. This thing in square brackets is a closure, and it understands value. But in this particular case, because this is a very simple control structure, and the compiler has inlined it. And it's inlined it into a Boolean test, so that there's a bytecode here which tests whether the result of less than is true, and jumps around to push false and return if x was not less than a point y. And then here's the inline closure here, push receiver, push temp, send y, etc. So the thing to notice here is that all access to instance variables is encapsulated. It's only possible to access instance variables of the receiver within the method, but the instance variable access is direct. Right? We're not sending accessor messages, we're actually reaching in and answering slots. And then another thing to notice here, apart from the fact that, okay, we've inlined this closure, is that there's no primitives. So unlike Java bytecode, where the arithmetic is in the bytecode set, and there are bytecodes for both integer and floating point arithmetic, there's no arithmetic here. There's no primitives in the bytecode. The bytecode is only for representing operations in the language, which are return, instance variable access, assignment, sending messages. And so the way that primitives are introduced into the language is by some metadata in a method. So here's the less than method for small integer, and small integer is one of the hierarchy of integer types, because we have stretchy integers, we can have infinite width integers, and small integer is an integer with a tag that fits in a machine word. And there's a primitive in the virtual machine that knows how to add those. And there's some metadata, and the syntax is actually, this is a message pattern that looks kind of like and colon, right? So this is a keyword with a constant as its argument. I don't want to say too much about the syntax. There's a lovely syntax which is mix fix. So you have three kinds of selectors. You have unary selectors, where you can just send some word to some expression that has the highest priority. There are binary selectors like less than and plus, which just have no precedence. So multiply is not higher precedence than less than. It's just strict left to right. And then you've got keyword messages, where you can have any number of keywords, each keyword ending a colon, in front of an expression, and the concatenation of all those keywords is a procedure name. So you can have quite complicated procedures that take multiple parameters, and it's very readable because you have a word in front of each parameter that explains it, instead of you having the one word and then the long list of comma-separated things that you have to go to the definition to try and figure out. What happens inside the VM, this is going to result in some kind of method object which has some bytecodes in it and some literals, the selectors for less than and etc. And what happens here is that the method object is very similar, but there's a little bit of state in it that says to the VM, I have a primitive and this is the number of the primitive. And so the VM has a whole set of primitives which can do the operations that are needed to bring the thing to life. So remember that instance variable access is direct. Okay, so Smalltalk has done live programming for a long time, and what does that mean? That means the ability to do schema migration in the live running object soup. So you have some class, and you are developing it, and you have instances of it floating around in the heap, and you want to add an instance variable to that thing. So you need to change the size of these objects. So the way that's done is by two primitives in the VM. One, all instances is something that causes the garbage collector to sweep the heap looking for all instances of a particular class and returns that as a collection. And once you have the all instances, we then want to mutate. So what the program environment itself can do is create a duplicate of the original class and recompile all of the methods, change the schema of the class and recompile all of the copies of the methods so that they all have the different instance variable offsets that they have. And then create, for each instance in this collection of all instances, create a new instance, corresponding instance, copy the state from one to the other, and the new instance has the new instance variable with nil in it. And so now we have two arrays. We've duplicated the classes, and we have two arrays of instances, and we want to exchange them, so that every reference in the system to the old instances is changed to a reference to the new instance. And if we do that with the classes and the instances, then the old system is no longer referenceable by the heap and will later be collected by the garbage collector. And poof, we've changed the system on the fly. So there's kind of two different ways of doing this. This is the two-way become, where all references to A become references to B, and all references to B become references to A. But you can also just as well do this particular example by having a one-way become, where all references to A are replaced by references to B, and references to B are not changed. I just want to go into a little bit of the history. Why did it start off with a two-way become? So when Smalltalk was implemented at Xerox PARC on the original Alto and the D machines, these were microcoded interpreters. So indeed, every time a message was sent, a context object was allocated. And one of the performance problems there is that, if you have some activation record and it's got some state, which are the arguments that are going to form if you output arguments that are going to form the input arguments of some message, and you create a new context, you have to copy all of that state across. So there's the overhead of creating this context, of copying the state across, and then having the garbage collector reclaim this context when you return. So you can see how expensive contexts were. But if you have a micro-coded machine, it can kind of make that kind of thing go fast. Well, an important part of the architecture of these machines were that they were 16-bit word-oriented machines. So the machine had a series of 64K word pages. And to address more than that, the Smalltalk designers, Dan Ingalls, came up with a 32-bit entry. So one of his pages in the system was divided into 32K 32-bit entries, where you could form a 20-bit address from a 16-bit word and a kind of a 4-bit page index. And that was how the heap was constructed. So there was one page, which was the object table, and up to 15 pages, which were the heap. So it was absolutely trivial to implement compaction by, when the garbage collector would reclaim objects, moving the bodies of the objects, which are referred to by this indirection, and then just updating this indirection. And so it becomes trivial to implement become, because if you have two of these guys, you can make this guy refer to the other guy by just swapping the entries. And a pointer in an object body refers back to the object table entry. So from the original constraints of the machine came this very natural way of doing this two-way become. And indeed, in Visual Works, this idea is retained. So inside the virtual machine now, even though there's no object table, there's like a classic new space and there's old space segments. Objects, when they're born, look like this, where there's a flag word that the garbage collector understands. There's a class reference. What's the class of this instance? Whereas in here it was like there's a size and a class and then instance variables. And then there's an indirection between the header and the identity of an object is the address of its header, and a pointer to the body. And when the object is born, these two are together, and then later on, when an object migrates to old space, it can be split into two, or when a become happens, it can be split into two. But the problem here, which is not such a problem when you're on the original machine, except the original machines were kind of slow. The problem here is that every time we access an instance variable, we have to take this indirection. And the JIT can obviously cache the indirection in a register between calls, but it's only if you get a series of instance variable accesses in between a call that does any good. And as you can see in the point example, the instance variable access is kind of rare. There's a lot of sends happening. So it's not very effective, and essentially the overhead is that every time you access an instance variable, you're going to have this overhead. So other Smalltalk implementers decided that they would not have this object table indirection, and instead have a flat object, and they chose to do this one-way become, where they would scan the entire heap looking for all references to A, and every time they found a reference to A, they would replace it with a reference to B. So you get fast instance variable access, but you get very slow become because you have to visit every pointer. And this is worse than all instances, because in all instances, all you're doing is accessing one field of every object to find out how big it is, to find out how you skip to the next object, and another field to find out what its class is. So it's like, on average, sort of an order of magnitude faster to do all instances than the become. So what we're trying to do is here try and avoid the cost of instance variable access and avoid slow become. So that's the problem we're trying to solve. So I need to explain a little bit about the history of the VM evolution to see how we solve that problem. So in early Smalltalk VMs, there's a heap, there's a set of primitives, there's the bytecoded interpreter, and there's the GC. And the first optimization that has to go in is something to speed up message lookup, because if every time you're sending a message, you grab the receiver, you grab its class, and you search its method dictionary, the thing is going to crawl. So the first optimization structure to appear in the VM is a simple associative cache between classes and message selectors, and the VM on every send computes some hash function of the class and the selector and looks that up in the method lookup cache. And only if it's not in the method lookup cache will it search the class hierarchy to find out the matching method in the structure of the class referring to its superclass and the class referring to its method dictionary. The whole system being this concrete example of using objects to represent code. So if you go to a modern Smalltalk VM, and of course, this is those of you who are current will know that this is not at all modern. This is like 20 years old. But anyway, what's added to this is we have a code zone, and we have a JIT compiler that compiles bytecoded methods into machine code, and the VM actually executes machine code. But being Smalltalk, we also have to do something about the cost of contexts. And so the really important thing that Peter Deutsch did in the PS compiler in '84, so it's older than that, but anyway, 20 years old. Is that the classic step was to realize that if you compiled the bytecode to machine code, you could implement append not as this associative lookup of the method lookup cache, but as a call instruction. You'd load some tag into a register at the send site, call a method, and the method would grab the current receiver and compare the class against the class loaded in at the send site. And if they were the same, continue. And so what happens there is that activation now looks like a traditional stack organization. And what we have to do is lazily create contexts when the programmer asks for them. So when a send happens, you don't create a send, you just create a stack frame, and execution is normal, and the output arguments overlap the input arguments. But whenever, for example, an exception happens and the program says to itself, I want to have a look at this context, we create an object which serves as a proxy for the stack frame. And so inside the machine, there's this small zone where we keep the most recent number of activations in a more conventional stack activation form. And we have these proxy objects in the heap context which can refer to them. And the stack zone has a limited size. It's not an infinite stack. It's organized as a set of pages so that when execution continues and we run out of some stack, what we can do is take a page of activations and evacuate it to the heap in the form of context objects and use that emptied page for new activations. So typically the stack zone might be 40, 100K. It's a very, very, very small amount of space. And it effectively works as a cache for the most recent N activations, or as a cache of activations between different lightweight processes. Now, the elephant in the room here is that there's no adaptive optimizer here. So how does this thing go fast? Well, I can't talk about the adaptive optimizer, but it's on its way. A great PhD guy who's doing an innovative adaptive optimizer, which is written in Smalltalk and entirely in the image above the virtual machine, rather like the Graal Java research VM. So that's coming, and that's why I put modern in quotes, because until we have an adaptive optimizer, we won't be competitive on performance. So okay, so I'm wanting to talk about evolution here. So a standard thing in evolution, you know, there's some selection pressure, and you can think of that as tests. You run your software, it's not fast enough, look at it, okay, think about it, let's try and do some stuff. But there's also this sort of bottom-up refinement that leads to bottom-up refinement. You can tune, polish, etc. But a much more interesting process in evolution is exaptation, which is this idea of a trait which has evolved under the standard selection pressures to solve a particular problem, which then gets used in a completely new way. And so we've already seen the method lookup cache was there to solve lookup speed, and the stack zone was there to solve the overhead of creating contexts. So, because I'm nuts, I'm going to tell you about my favorite example of exaptation in human evolution. And there's a theory called the Aquatic Ape Hypothesis, which says that when we were Lucy-like, between 7 and 5 million years ago in the Afar Triangle in Ethiopia, we were trapped by rising seawaters. We were arboreal, but the rising seawaters meant that we could no longer get to the ground to feed. We could live in the trees, but we actually had to start swimming and catching seafood. And as we caught seafood, our diet became rich in omega-3 fatty acids, and our brain doubled in edge, quadrupled in area over the chimpanzee brain, and we became humans. But one thing that we had to do was learn how to control our breath so that we could dive to catch shellfish, etc. And good breath control is the pre-adaptation that you need for speech. So breath control was exapted for our communications method. And if you look at chimpanzees cannot hold their breath. They have no control over their breath. If you have a look at dolphins have evolved so far in their breath control, because they were originally land mammals, that they can no longer voluntarily breathe. So when we fall asleep, we're unconscious. It's a voluntary system, an automatic system in our brain that keeps us breathing. Dolphins have evolved beyond that. They've lost that, which is why they have to sleep with half of their brains, because if they didn't, they would stop breathing. So what we're going to do is exap the method cache probe and the stack zone and the primitives to give us cheap become. So this isn't the first time that anything's ever been exapted. There's a really nice thing which leads to the current crop of VMs, which is this inline cache, this idea of having a register load and a call instruction to optimize message sends, gave us the first fast dynamic language VMs on stock hardware. And when the Self team adapted that technology for Self, which has a much higher degree of polymorphism, being a prototype language, they solved that by, instead of just having the one cache, which would have to be rewritten a lot in polymorphic send sites, is when they discovered, the second time you tried to bind a send site to a new class, you would introduce a little table, a little jump table with cases for each class called the polymorphic inline cache, and that sped up Self. But the insight was that, this optimization structure is actually recording type information in the program for us, and it's saying, okay, on a monomorphic send site, we know that there's only one class, but on a polymorphic send site, we know that there are some number of classes. And the insight was that we could then use that to do adaptive optimization. If we introduce counters, the program can then stop itself when it finds a hotspot, and it can look at the caches to find the concrete send data and inline on the basis of that, and continue. So that's another great example of expectation, I think. So what we're going to do is make become be lazy, and have the ability that any object can become a forwarder, and arrange that we're going to trap when we do a message lookup, and we're going to avoid the cost of a read barrier on instance variable access because we're going to scan the activations in the stack zone. So if you look at Lisp VMs, when they were built on their own hardware, they had read barriers in the hardware so that the copy and garbage collector didn't have to do a following step, that the following could be made lazy. But we're trying to run on stock hardware. We don't have any support for such a hardware read barrier. And if we were to put in a read barrier everywhere we access an instance variable, we would both slow down instance variable access, but also we'd blow up the amount of code that the JIT creates, because the sequence to fetch the class and check that the object's not forwarded is large. So, okay. So we can avoid that. Just a little bit on the object header format. It's really important if you're going to do 64 bits that you don't just double the size of that object table to get 3 64-bit words. Instead, try and keep things small. So here we've got direct pointers, so we have no indirection, and wasting 64 bits on a class reference is crazy, so that there's in this system a 22-bit field. We can have up to 2 million or 4 million classes, 4 million classes. And so what represents a class in the object is an index into a sparse table of classes. And all of the inline caches use these class indices as tags, which is nice because they don't move. The garbage collector doesn't move them, etc. They're not true objects. And the way that we make instantiation fast, so that when you send a message to a class to create a new object, you don't have to find out what its index is in the table, is that in a class, its identity hash, the one hash that will not change even if the object moves, is the class index of its instances. So when you instantiate an object, you just copy the identity hash of the class to the class index. So okay, so here's become. It's very, very simple. We have 2 objects. We want to become them. If they're the same size, we can just interchange their contents. But if they're not the same size, we create 2 copies, and we convert the originals into forwarding pointers. So we change their class index to the class index that will never be bound to a class that is reserved for forwarding objects. And we always arrange that objects have at least 1 pointer. So we can't have just a header. A zero-sized object has to have 2 words in memory. And then we just set after we've copied the contents, we set the 0th field in the originals to point to the new copies. Then we, if what we became were objects that can have instance variables, because things like an array of bytes can't have instance variables, so there are exceptions. But if we became an object with instance variables, we scan all of the activations in the stack zone, looking for just the receiver reference in each stack frame. So we're walking the static chain. We're not scanning every field in the stack zone. We're walking the static chain of activations the dynamic chain in the stack zone, and we're updating the receiver pointers of any that referred to a forwarder, so that there's no need for a read barrier when we access instance variables. So let me go through this in a little bit more detail. So you've become some objects, and that may change some objects which are referenced on the stack into forwarders to other objects. and then the bytecode is marshalling some set of pointers for a send, and 5 minutes, right, I gotta go, good. So you send, and what's gonna happen is when you do the method lookup cache probe, it's not gonna match because the class of the object is a forwarder. And so the following of the forwarding pointers is moved to the failure side of the method lookup cache, which is a very rare thing. So we co-opt the message lookup binding failure side to follow forwarders. And then primitives in Smalltalk have this lovely feature that a primitive is associated with a method. So what the primitive can do is compute the result of the method or fail. And if it fails, then the rest of the method is executed. So what primitives have to do is, if they're to fail without side effects, is that they have to completely validate their arguments. So they always validate their arguments anyway, and since they're validating, they will always fail when they find a forwarder. So we can again follow forwarders when we have primitives that encounter forwarders by moving the code to the primitive failure case. So here's an example. Here's the primitive. Here's the structure of a cursor in Smalltalk. So there's a subclass of form. So there's a bits, width, height, depth, offset, and then a mask. So this is the image of the cursor, and here's the hotspot in the cursor, and that's a pointer to the bytes. And then there's another form, which is the shape of the cursor. And so before the primitive can install a cursor, it has to walk that structure and check that everything's of the right type before it can install the cursor. And if it finds a forwarder, it's going to fail. So the thing we need to do is know that this primitive accesses its object graph to depth 3. And then when it fails, we can traverse the argument graph to depth 3, and if we find any forwarders in that structure, we can follow them, fix up the graph, and then we can retry the primitive. So the lazy following of forwarders in primitives is done by being able to know what the depth of the graph is. Okay, so what's really fun about this VM is that it's a Smalltalk program. So here I've got a Smalltalk system, and this is the simulation of the VM in Funky Squeak, where you can actually twist windows, and inside the simulation I've twisted a window back. And so this is like a list of information from the execution of the VM, and the VM is just this Smalltalk program, and the way that we get it to work is that we have a CPU simulator which executes machine code, so when we're developing machine code it's completely safe. You're not down in GDB, it can't break. You can ask the CPU simulator to remember the last 1,000 instructions that you executed when you have a bug, if you want to try and figure out what happened, etc. And there's a Smalltalk to C translator, which converts the Smalltalk into C, and that's compiled to produce the production VM. So the way that we compute those accessor depths for primitives is just by adapting the parser in the Smalltalk to C translator. Okay, one other cool thing. You're trying to debug a garbage collector. How do you do it? You know, garbage collectors rewrite graphs, and if they rewrite the graphs wrong, you have just this scramble. But this is just a Smalltalk program, so it's easy to copy the entire VM before you run the garbage collector and kick the copy over the cliff and see whether it survives. And if it doesn't survive, it falls dead, and you have the original that you can then clone and run again and continue until you've figured out what the bug in your garbage collector is. So the way you debug garbage collectors is you kill more lemmings. So, okay, finally got to the end. So the performance, this does indeed work. This VM, which to all intents and purposes is the same as VisualWorks in terms of the quality of its code generator. It's a little bit better, but basically it's the same. Really the difference is this Spur architecture, direct pointers, and this lazy read barrier, and we're already getting 40% faster than VisualWorks, and a binary trees benchmark from the computer language shootout is exactly twice as fast. And the adaptive optimizer, which we're calling Sister or Scorch, is on its way. We're starting to see results from that, and that will be released next year, but there's loads and loads of work to do in the context of that, floating point, et cetera, et cetera, et cetera. So, you know, we have a modern supported open source Smalltalk VM, which is in use by the Squeak community, the Faro community, the Newspeak language community, Raspberry Pi. The latest release of Scratch on Raspberry Pi is Spur. Spur is on its way to the space station in a Raspberry Pi, and you can go to my website and see the other projects, all of the projects that we've got going on for the VM, which are all unstaffed. Please visit, please staff them, and you can find out how to build an image there. Thank you.